Well, hello all. Today, grade 12, Le Chatelier's Principle. Sounds French to me. I hope it's not French to you by the time we finished. A change in any of the factors that determine the position of the equilibrium in a system will cause the system to change in such a manner as to reduce or counteract the effect of the change. Woo! It's on page 421 of Study and Master, and on page 214 of Study and Master, we get an example of Le Chatelier's Principle. If we have reactant A and reactant B go to form reversibly product C and D, then let's see how we can apply Le Chatelier's Principle. So, let's take something that we dealt with in the first term. CH2COOH, lovely bit of revision there. Anything that ends in COOH, carboxylic acid, isn't it? So this has got 2 carbons. It must be methane, ethane, propane, butane, pentane, hexane, heptane, octane. But we only have to go as far as methane, ethane, but it's ethanoic acid. Ethanoic acid combines with, look at that, ends in OH, it must be a, OH must be a, and it's got 2 carbons, it's an alcohol, methanol, ethanol, okay, ethanol. This is methanoic, ethanoic, propanoic, butanoic, pentanoic, hexanoic, heptanoic, octanoic. That's how we know it from our song we learned, right? Ethanol goes to form, now what is an oic acid and an alcohol go to form, or carboxylic acid and an alcohol? It goes to form a girl's name in the Bible, Esther. What's the ester? Well, methyl or ethyl ethanoate. Ethyl ethanoate. So that's the ester. Goes to form reversibly, and water. Now, it doesn't say so in your book, but this would be aqueous. It's got to be dissolved. That would be aqueous, or your alcohol's dissolved, and your ester would be aqueous, and your water would be a liquid. Okay, aqueous, 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 and liquid. Now, how do we apply Le Chatelier to this? Well, first of all, you see we've got a system. And our system consists of a beaker in which we're going to pour, first of all, we're going to have some ethanoic acid, and we're going to have some alcohol. But those are dissolved in water, they're not pure. So we're going to throw those in, ethanoic and ethanol, we're going to throw those into our well, I'm lying. We're going to throw them into a test tube in the beaker. So these are going to be thrown, I'm forgetting, it's been a while. We throw those into a beaker, a test tube, and there are our dissolved things, and we put it in a hot water bath. And so there is our alcohol and our acid. Now, at first, how much ethyl ethanoate do we have? Now, they use it as a solvent to dissolve substances. So suppose we want to make ethyl ethanoate, and we were to now draw a graph of time as our time. Whoa, I'm getting dyslexic. Time in seconds, and concentration in moles per decimeter cubed per, or decimeters to the -3. Okay, if we start, I'm going to just call that's going to be A, that's going to be B, that's going to be C, and that water is going to be D. Okay, what is our concentration of ethanoic acid when we first throw it in our system, which is the test tube? Forget the beaker, nothing goes out of this test tube. The beaker's just there to heat it up. Well, we're going to have quite a bit of A. Let's just say that's quite a bit. There's naught, there's no time, and then this goes on for, I think it was a few minutes. It's been a while, I've forgotten. But let's say there's quite a bit of ethanoic acid, or A. Now have a look at a graph of our reactants and our product. That would be our acid, our alcohol, and our ester. This would be a typical graph showing the progression of the concentration over time. Concentration of the 3 over time. I think we used to leave it in the water bath for about 5 minutes. Okay, at first we start with a lot of acid and a lot of alcohol. And then as time progresses, they both get used up to make our ester. But as time goes by, this reaction is reversible and it goes backwards as well as forward. And eventually the forward rate equals the reverse rate, and that is when our graph is level. So do you understand that there comes a time, if you have a reversible reaction, which is when Le Chatelier applies, that there will come a time when all the graphs go horizontal. They are parallel. Okay, now, classical question. Suppose you see a spike like this of B. What does that mean? It means you've taken your test tube and you've done what? B was the alcohol. And we've thrown suddenly a whole lot more alcohol in the test tube. We disturbed the equilibrium. We've disturbed the system. Now, Le Chatelier says that because you have a disturbance, it's like a seesaw, you've added more B, the seesaw is slowing down, we've got to somehow get the seesaw back up. And that is, we've got to get more C formed and less A and B. So B is going to decrease after it was added, but to decrease B, we've got to also use up the acid. So B and A react together, they both decrease, and notice what happens to, again, our product. Suddenly the more product is formed again, till eventually all 3 graphs become level again. So here we're seeing the Le Chatelier as exhibited by our graphs. A change in B, an increase of B, will cause our system to want to get rid of B, get rid of A, because those were our reactants. Well, it wants to get rid of B, but to get rid of B, it's got to use up B and A to form C. So B and A decrease, our reactants decrease, our product increases. So eventually, forward and reverse reaction rates will again be the same, and a new equilibrium will be formed. And then, let's see, when you see a spike of this again, what was this? This was the acid. Suddenly more acid was thrown into the test tube. Not more alcohol, just more acid. You see that spike there? Le Chatelier says, get rid of that acid, get rid of the acid. How do we get rid of the acid? Well, if the acid reacts with the alcohol, that'll get rid of the acid. Okay, fine. So we get the acid and the alcohol react again, they decrease, and more C is formed again. So the acid plus the alcohol, their concentrations go down till a new equilibrium, a new straight horizontal graph is formed, and C will rise, and slowly it'll become horizontal again. And the moment a graph is horizontal, it means the rate of the forward and reverse reactions is the same. So if the rates of the forward and reverse reactions are the same, you're not getting a change of concentration. So there you're seeing Le Chatelier applied there and Le Chatelier applied there to bring our system back into equilibrium. And that is why Kc is a constant. If you increase, say, B, to keep Kc constant, you've got to get rid of the B by forming more C. But to get rid of B, you've got to use more A as well. So A and B decrease, C will increase. I mean, if you added more C, you're going to have C decrease and A and B will increase. So that is how it will apply. So there we see an example from a reaction we've used, and that is an application of Le Chatelier. I just want to correct, our ethanoic acid is CH3COOH, not CH2.